Imagine tying a stone to a string and swinging it in a continuous circle around your head. If we attach a tiny light, it traces a perfect and continuous repeating path. This repeating circular motion is the mechanical foundation for signals that power digital audio, for wireless telecommunications, and medical imaging. It generates sine and cosine waves. It defines the behavior of complex numbers and Euler's formula. It is the core logic inside the Fourier series and the fast Fourier transform. Most students struggle with signal processing because they are forced to memorize pages of abstract algebra, but those formulas are actually descriptions of pure visual geometry. Everything in the Fourier transform comes from a single point rotating around a circle. Master this spin, and the equations describe what you already see. To see how this works, we need to define exactly what rotation is before we touch any advanced math. Rotation means a point moves, while two conditions never change. First, the center of movement remains absolutely fixed. We call this the origin. Second, the point maintains a rigid distance from that center, called the radius. This length is locked. Because the origin and radius are fixed, only one thing changes: the angle. By tracking this single changing angle against our unyielding radius, we establish the parameters needed to map any frequency. To track this rotating point mathematically, we have to stop it from moving. We freeze the spin so we can map its precise geometric location on a grid. When we freeze the point, we can drop a vertical line straight down to the horizontal axis. This forms a right triangle, allowing us to pinpoint the location by its horizontal x and vertical y coordinates. This formula shows how the fixed radius mathematically binds those horizontal and vertical positions together. The radius equals the square root of x squared plus y squared. It is the Pythagorean theorem applied to a circle. We can see exactly how this locks the geometry by plugging in actual dimensions. If a triangle has a horizontal base of 3 units and a vertical height of 4 units, squaring and adding them yields 25. The square root of 25 is exactly 5. The spatial layout is now strictly bound. No matter where the point travels along the perimeter, its distance from the origin is definitively tied to its horizontal and vertical shadows. In signal processing, we usually don't have those shadow lengths. We only know the radius and the current angle. From those two pieces of data alone, we have to extract the exact x and y coordinates. This diagram shows the two trigonometric equations that solve this problem. The horizontal position, x, equals the radius multiplied by the cosine of the angle. The vertical position, y, equals the radius multiplied by the sine of the angle. Let's test this on a specific coordinate. We have a radius of 10 units, currently rotated to an angle of 60 degrees. To isolate the horizontal position, we take the cosine of 60 degrees, which is 0.5. We multiply that by our radius of 10, giving us a horizontal length of 5. To isolate the vertical position, the sine of 60 degrees is about 0.866. Multiply that by 10, and we get a vertical height of 8.66. These equations give us absolute geometric certainty. By filtering our radius and angle through sine and cosine, we map a signal's exact amplitude at any specific phase. Up to this point, we have relied on a static angle, but physical objects and electrical currents do not sit frozen on a graph. They exist in continuous, dynamic motion. The angle is constantly changing because it is entirely driven by time. To bridge static geometry into physics, we map the angle by taking the angular velocity, which is the speed of the spin, and multiplying it by time. If the angular velocity is 2 pi, then exactly 1 second later, the total angle is 2 pi. The point has completed one full revolution. We have now built a time domain system. The precise angle of our point is continuously generated by the ticking clock. To make this practical, we have to quantify that rotation speed. We call it angular velocity, denoted by the Greek letter omega. This formula links the angular velocity directly to standard frequency. Omega equals 2 pi multiplied by the cycles per second. If we measure a real-world frequency of 5 Hz, we can drop that straight into the equation. 2 pi times 5 gives an angular velocity of 10 pi. When calculated out, that equals approximately 31.416 radians per second. This number tells us exactly how far the point travels. It sweeps through roughly 31.4 radians of angular distance along the circle every single second. By calculating angular velocity, we can perfectly predict a signal's exact geometric location at any given millisecond. Now we combine the pieces. To see where the waves of the Fourier transform come from, we must look at the horizontal and vertical movements in strict isolation. Ignore the vertical movement. Watch only the horizontal projection as it slides back and forth along the axis. When we take that purely horizontal back and forth motion and plot it steadily forward across time, it draws a perfect cosine wave. Shift your focus to the y-axis. Ignore the horizontal and track the purely vertical projection bobbing up and down. When we take that vertical bob and plot it forward across time, it traces a perfect sine wave. Sine and cosine waves are the one-dimensional shadows of a point rotating in two-dimensional space. By replacing our static angle with angular velocity and time, our mapping coordinates are complete. The horizontal position is the radius times the cosine of omega t, and the vertical position is the radius times the sine of omega t. If we treat these horizontal and vertical positions as the real and imaginary parts of a complex number, we have the coordinates required to define the complex plane, the mathematical environment where Euler's formula operates. All of this mathematics traces back to the pure physical geometry of a stone swinging on a string. Mastering the geometry of this single rotating point provides the fundamental blueprint for the entire Fourier transform.